All right, everyone. My name is Vincent Ledvina, and I'm going to essentially recast my Aurora Summit 2024 talk here for my website, blog post, and just for posterity. If anybody wants to watch this later down the road, feel free. I was trying to record this during the actual summit, but it didn't work out due to sort of some technical difficulties. So I'm just going to run through it now. And yeah, the final version will have hyperlinks and other things where you can sort of click around and all that. So if you don't see those here in this presentation, in my blog post, which will be hopefully linked underneath this video and wherever it gets posted, you'll be able to find the version of the presentation which you can then go through and then um, click all sorts of links, like links to my ebooks and blog articles, specific cameras that I recommend, things like that. So, yeah, without further ado, let's get into it. So, the title of this talk is Aurora Forecasting for Any Skill Level, and I presented this. Now it's been about a week since the Aurora Summit. So, it was a great talk, and I thanked Melissa and Dixie there, but I just want to thank them again for inviting me to give this presentation at the Aurora Summit this year. So here's what I'll be talking about today. It's very simple, similar to last year's talk, although it's been updated with some key details. So first off, I'm just going to give an introduction of who I am. Then I'll go into what space weather is, what the aurora is, what causes the really, really good aurora shows that we see, and then really get into some, thoughts about how to predict the aurora and also some aurora chasing strategies. So I'm not going to really spend a whole lot of time on this because I'm assuming that if you're on my website, you can just click around, go to the About tab, for example, and you can read essentially this entire origin story of how I got into auroras. But just to run it back really quick, I saw my first aurora in 2003 when I was 4 years old, and this was during the Halloween storms of 2003, so October 31st to roughly November 4th. In that period, there was some pretty extreme space weather. And I remember seeing the aurora trick-or-treating, going home. I'm from actually the Twin Cities in Minnesota, and I grew up there. So I remember just going back to my house in Maplewood and looking out over the Mississippi River Valley and seeing northern lights. And it was pretty incredible. That really just gave me this passion for the night sky, the outdoors, science in general. I was in Boy Scouts, became an Eagle Scout, was always outdoors camping and just loved doing that. Um, Became interested in photography, just sort of on family trips. I would bring old cameras that my dad or other people would sort of lend me. And it was just really fun. I liked taking pictures of my surroundings and sharing what I captured then with other people. And I think that's really what brings me joy in photography is, you're able to go out in the natural world and take pictures of stuff and then show that to other people and they can like enjoy uh, sort of, a piece of what the emotion you felt was at the time that you were taking the photo. So, essentially I could take a photo of the night sky and yeah, I was just so into it and people would say, wow, that's super cool. And like I could tell them about it and it would just segue so nice into this conversation. So, I really think photography is one of those things that it's not only an art form, but it's also a way that you can express emotion and sort of convey a story. So I eventually became interested in aurora photography. I think that's kind of like the pinnacle of astrophotography. It's, you're not just going out into a field and looking at the Milky Way, which is always there, and it can be predicted for thousands of years in advance, but you're actually looking at the data, space weather data, and having to interpret that. And you need to know a little bit more about the science to really spot northern lights down at mid latitudes, like I was in Minnesota. So, yeah, I took my first aurora photo when I was 16, moved to North Dakota to study physics at UND. And then, kind of by happenstance, I just got this Aurora guy moniker. At University of North Dakota is when I really started caring about, posting on social media. I wanted to share my photography with a wider audience. I was like, okay, I kind of know what I'm doing now. So in 2019, I created my Instagram basically, and UND posted one of my photos, and it became really popular. It actually became their most liked photo ever at the time. Not sure if that record still stands, but I was famous on campus for a weekend essentially, and people uh, started coming up to me asking me, "Hey, are you that Aurora guy who took that photo? Hey, are you that Aurora guy?" And the first time it was just, "Hey, are you that Aurora guy?" And I didn't know what that meant because I wasn't thinking I was known or anything like this. So I asked, "What do you mean?" And then they showed me that post that you can see here on the right, and I said, "Oh, okay. I guess I'm the Aurora guy." And my friends really drove that home too. They wouldn't stop making fun of me for it. So yeah, I was really involved on campus with the astronomy club. Did a lot of internships in undergrad. University of North Dakota didn't have any space physics programs, so or any sort of curricula or faculty. So intern at the National Solar Observatory, which is a picture of me in the back there from 2019, and then later at Aurora with Dr. Liz McDonald and Laura Edson, and then later on at Predictive Science Incorporated, where I did some CME modeling. So a lot of Aurora chasing adventures over the years. This is in Churchill with some friends, Justin Anderson, Elisa Ferguson, Donna Locke, RJ, Roldan, a few names that you might recognize. So I've seen lots of wildlife and animals, polar bears included. This is from Churchill, Manitoba in September of 2022. So I just really think the Aurora is beautiful, right? And being underneath the Aurora has granted me some really unique and exciting experiences. I saw my first high latitude Aurora when I was in Fort Yukon in March of 2022, and actually the photo you see on the right is seen as a video on the left. So just shows you how dynamic, incredible, and just jaw-dropping the Aurora can be. I mean, this display right here is still one of my top 10 ever. And it was just a minor, KP4 coronal hole high speed stream, nothing, nothing noteworthy from a space weather perspective. But this was the first Aurora I had seen at this time that really just made me drop to my knees. I was um, just so taken aback, and it was emotional. So this is what actually convinced me to move to Alaska this night right here. And I was up participating in this sounding rocket mission called the Velocity Aurora Microburst Pulsation Sounding Rocket. So it was just a really great night. We launched the rocket into the pulsating Aurora after this substorm. So just wanted to highlight that. So now I'm a space physics PhD student here in Alaska. I'm actually recording this from DC right now. I'm here on some like NASA business, but mostly living in North Pole, Alaska. I think I've actually spent less time in Alaska over the past year than in Alaska because of all the traveling I've been doing. But that's where my residence is in Alaska. So I share my love for the Aurora, and I just love the Northern Lights. I love the Aurora. I just love all aspects of it. It's so powerful. It's not just, incredibly important for science, but it's just an amazing natural phenomenon. I mean, I could do this stuff day in, day out, night and day. I could do the Aurora as long as I'm alive, and that's kind of what I plan on doing. So I'm more or less obsessed with the Northern Lights and the Aurora. I'm a photographer, professional photographer, citizen scientist, and I'm researching these things right now called auroral beads. So I don't know if this will play, but this is a kind of a nice video that I did with the Aerospace Corporation, which is also where I'm interning right now, talking about my research with auroral beads. But that'll be hyperlinked in the sort of website version of this talk. So auroras are a part of space weather. Just like there are clouds, rain, and wind on Earth, space has weather too. And what is space weather? What's the sort of operational definition that we have? Well, space weather refers to conditions around a star like our sun and its interplanetary space that may affect space and ground-based assets as well as human life. So this is actually taken right from a publication that I'll have linked in the final presentation that I led, and we investigated space weather phenomena and their effects on daily life here on Earth, technological assets in space and on the ground, and also humans as well. So if you're looking for more information on that, it's a Ledvina et al. I think it's 2022, and it's I can never remember the full title, but it's if you just Google Ledvina et al. Interdisciplinary collaboration and space weather, it should pop up. It's a Frontiers publication. But really, when I talk about space weather, I really like to just show a picture of the aurora, right? Just what is space weather? Look up if you're in Alaska, right? Look up every single night. There's space weather in action. right above your heads. And that's really because, the aurora is a perfect marriage between what's going on in outer space and what's going on the ground, right? You have the influence from the sun eventually hitting our atmosphere, then you have the Earth's response as the aurora. So it's kind of, taking these two halves and merging them together into one phenomenon that we can all enjoy and study and witness and be amazed by. But of course, it's more than that, right? It's not just auroras. We have shock waves. We have million-degree plasmas. We have giant magnets in space. We have incredible space missions like Parker Solar Probe. We have solar flares. We have prominences, sunspots, active regions, coronal holes. All sorts of things going on. CMEs, explosions. Space weather is a really exciting and incredible field to just either enjoy or, in my case, to really be a part of and have the privilege of studying. I'm really enjoying it. And it all starts with the sun. Just like the sun creates weather here on Earth, clouds, wind, storms, rain, etc. The Earth also is affected by weather from the sun in space. So, the sun is really responsible for the space weather that we experience here on Earth. And here's what the sun looks like to us on the ground. This is a picture of the sun, right? Don't look at the sun. Not advising doing that. But scientists have sort of special sunglasses. Scientists can look at the sun in different wavelengths, not just visible light, right? This is visible light here. But as soon as you put on some ultraviolet sunglasses, you're able to see the sun in a way that might not be familiar. So, this is sort of this continuum right here that I'm circling with my cursor. That's sort of what we see, right? If you were able to take solar glasses, put them on your eyes and look at the sun, you wouldn't get all this glare. You would just see a ball, a disc rather, something like this, orange or white. Maybe you'd see some sunspots on there, but you don't get to see the sun and all these other cool colors. And these are also colored images just to sort of be able to separate them. But we have spacecraft that are able to see, all this light that's really, from 1700 angstroms to 131 angstroms is mostly blocked by the atmosphere. So it's impossible to get these images from the ground. So we have spacecraft that have special filters on them that are able to see the sun's atmosphere. So when you're looking at the sun and you put on solar glasses, you're really only seeing the sun's surface. But as soon as you go to the sun's atmosphere and start imaging in ultraviolet wavelengths, you can start seeing things like the influence of magnetic fields. You can see hotter plasmas. You can see things that are lifting off the sun, like coronal mass ejections, big bursts of energy like solar flares. So, if you keep seeing these colored suns, right, we have different calcium wavelengths here, or rather emissions from calcium emission lines for absorption emission lines, something like that. Not a solar physicist, but these, as soon as you get to these different colors, these different colored suns, you get to see a lot more going on. And the sun is dynamic. And when you look at what's going on with these special sunglasses, you realize that there's, a lot more under the surface, or rather, below the surface that meets the eye. So, we're seeing tons more things going on here. Filaments lifting off, solar flares, like a big prominence eruption right there, solar flare and CME. And yeah, just a lot of really cool and interesting things, right? The sun is not static. I think that's the main point here is the sun is not static. It's not just this ball of light you see in the sky that doesn't change, doesn't move, doesn't do anything. If you put on these special sunglasses, you can see that the sun is constantly changing and it's creating weather, right? Weather is stuff that happens every day, every minute, every hour, every second. And the sun is certainly responsible for these dynamic conditions that create weather that then influences everything in our solar system and beyond. So part of this weather is this thing called the solar wind. Just like a hot cup of coffee releases steam off the top, the sun also just kind of sloughs off its atmosphere and it just sort of becomes less dense. It sort of disappears to our eyes and it eventually flows out into space and envelops all the planets and other bodies in our solar system. So, of course, the sun gives us warmth and life, but it also gives us space weather. And a lot of the space weather is then tied around this idea of the solar wind. So it's not just steam, right? It's not this hot cup of coffee. It's not, the sun is kind of like that, right? If you imagine a hot cup of coffee, you have steam coming off the top. The sun would be like that hot cup or that, body of liquid that's radiating all that energy and that heat and that steam. But instead of steam, it's really charged particles with magnetic fields. So, just kind of imagine like tiny little bar magnets in space, just all flying around. And normally this wind is calm and gentle, so it gives us space weather, but it's usually not that bad. But sometimes that wind can become really strong and fierce. You can get really fast gusts of wind or really long periods of fast solar wind. These things called high speed streams. And this solar wind, if it hits a planet with a magnetic field and a magnetic shield, which extends out into space, which we call a magnetosphere, the charged particles and magnetic fields in the solar wind can then interact with this force field. And Earth has its own force field created by the internal magnetic field. You have a compass in your hand and it points north. That's a magnetic field. And that doesn't just stop when you leave the surface, it extends out into space and forms this protective bubble around us, which we call the magnetosphere. And the solar wind tries to push up against that. But luckily, a lot of that flow, a lot of that wind is deflected around our magnetosphere, kind of like a rock in a stream of water. And we get this teardrop shape, which we call this is the bow shock here. The magnetosheath is sort of all these little curly bits and like weird swirls, and then the magnetopause. And then off the screen, potentially extending many hundreds of Earth radii is what we have called the magnetotail. That's sort of outside the scope here, but just to give you an idea of these different names and phenomena, which you may have seen before. This energy from the solar wind mostly is deflected, but depending on the orientation of the magnetic field, which we'll get into later, some of that energy can get directed inside, penetrate into our force field, and that energy gets funneled down over our polar regions, which then, of course, becomes what we know as the aurora. So what is the aurora? Well, there's really, a lot of qualities of the aurora that you could use to describe it, but it's nature's most spectacular light show. It's a piece of identity for many northern cultures. It's captivating, mysterious, and awe-inspiring. But technically, it's light emissions caused by charged particles from outer space, streaming along Earth's magnetic field lines, colliding with gases in the upper atmosphere. And auroras are created in a layer of Earth's atmosphere called the ionosphere. The ionosphere is one of the highest layers in our atmosphere. So if you look here on the right, you have the troposphere, which is really where all weather occurs on the ground, or at least all weather that we can really feel and experience on the ground is created in the troposphere. Planes really fly at this edge of the troposphere and the stratosphere. But auroras start occurring 15 to 50 times higher than a plane flies. So around 150 to 500 kilometers in altitude. So we're talking about a very high layer of the atmosphere. And if you notice that the ionosphere is sort of divided into multiple layers, the aurora really occurs in these E to F regions. And the ionosphere is called the ionosphere because it's full of ions. It's full of charged particles. So, we're used to breathing, O2 and N2 here at the ground, but as you go higher up, those molecules start to dissociate into their atomic counterparts. So we get O plus and N2 plus and other different ionic sort of species and different charged species. So the ionosphere is where these interactions between charged particles can create different phenomena, can create light in the case of auroras. And that's what happens is you have charged particles now from outer space that come raining down, again, another space weather term, come raining down into our atmosphere and sort of like a Plinko board. They're sort of hitting all these gas molecules on the way down before they eventually lose their energy and just fizzle out. But along the way, they're colliding with all these different gas molecules and releasing light in specific wavelengths corresponding to the type of molecule that they interact with. So above 120 miles, we get red aurora. That's caused by O plus. We get O plus at lower altitudes that causes green. That's sort of the most frequent color that we see. And then below that, we have this diatomic nitrogen fringe, which if the particles have a lot of energy, they can make it all the way down to these lower altitudes and then excite this nitrogen layer. So different colors in the aurora, just to reiterate, are due to different gases being excited or ionized by charged particles from outer space, or like surfers because they ride along these magnetic field lines. So if you imagine a bar magnet, you have these two areas at the north and south poles of the magnet where all the field lines sort of come together. If you imagine like a bar magnet and like the iron filings experiment you might have done when you were a kid or in grade school, these sort of weak points in Earth's poles, or I guess sort of above Earth's poles, are where the magnetic field lines then funnel all these particles down into, which then creates these auroras over the auroral ovals, or sorry, in the form of auroral ovals, which I'll get to in a couple slides. So just really quick, this is actually the same process by which neon lamps work. Is you have a gas in a neon lamp, which is then excited by some sort of electricity, and that creates light. And then you can have different sort of colored, glass tubes or whatever to create the different colors in a neon lamp. So, neon gives you a specific emission, just like oxygen or nitrogen. But in this case, we don't have electricity from a wall outlet and a cord. We have electricity from space. So, is the aurora like a giant neon lamp in the sky? Well, I would say so. So the auroral ovals occur over both the northern and southern hemispheres. We have the aurora borealis in the northern hemisphere, aurora australis in the southern hemisphere. And I see aurora every single night that I'm in Alaska. Making sure that it's clear and dark, but that's because I'm underneath one of these auroral ovals. So the reason why these ovals exist is that, like I said earlier, the north and south poles are where these magnetic field lines all come in to Earth's polar regions, and that's where all the aurora particles get funneled down into, and it creates this ring of aurora, sort of centered around 68 degrees geomagnetic north and south, roughly. And you get these kind of thin ovals of aurora that are constantly there at all times. This is important, as the auroral ovals are always there. Even when space weather is very, very calm, you still have a very, very tiny auroral oval. And it does fluctuate. If the solar wind is sort of flowing, pretty evenly or pretty average, that auroral oval is going to rest over places like Fairbanks or, Coldfoot, Fort Yukon, Yellowknife, Churchill, Tromso, Reykjavik, all these places. This is why, all the places I just listed are sort of advertised as, go there to see the aurora, because the auroral oval, under mostly quiet conditions, is right above these areas. So, when space weather becomes more active, these auroral ovals expand, of course, and get more active, and then you can see the aurora from further away from the poles. So, underneath the auroral ovals, you can see auroras every single night as long as it's clear and dark. And this is something that doesn't get talked about enough, is that there's patterns to auroras. And this is not just for high latitudes, but also during geomagnetic storms, when we have auroras at mid latitudes, we go through something called a substorm cycle. And I'm going to have a blog article on this later on my website. I'm still working on it because it is fairly complex. And the reason why a lot of, aurora chasers or space weather enthusiasts or, aurora Facebook groups don't talk about substorms is because even scientists don't really know how substorms work. But we do know how they present in the aurora. And this is, a pattern that's been known about it's been known about for a long time, but has been written about in the scientific literature since the early 1960s. You can go back, I think there's an Akasofu, Shin Akasofu was a professor at the University of Alaska Fairbanks. I've actually met him. He wrote a paper back in 1964 about this substorm sequence, which starts out with a growth phase where you see these thin auroral arcs stretching across the sky from east to west. So if I pause this video on the right is an all-sky camera field of view, so it's a circle. And imagine you're laying down, you're looking up at the sky. North is actually to the bottom here, and south is to the top, and then east is on the right, west is on the left. So sort of imagine like a fisheye, fisheye, like planetarium, sort of fish bowl, maybe, field of view. Anyways, you start seeing these arcs stretching across the sky east to west. These are the growth phase arcs. These eventually form little auroral beads on them in the course of 1 to 2 minutes in what's called a substorm onset phase. Boom. It's really hard to catch because, we're speeding up time here, but all of a sudden the aurora goes from nothing. I mean, this isn't nothing, but for me at least, my standards are a little bit higher now after living in Alaska for a couple of years. This is maybe worth getting out of bed for. I don't know. Anyways, I would know that this is a growth phase, so I would actually be staying up waiting for the onset and the expansion. But essentially you have these arcs that are just quasi static, evenly spaced, just kind of well behaved arcs. All of a sudden it grows these auroral beads. Boom. I mean, okay, it's really hard to pause the video at the right moment, but you get the idea. You get these auroral beads like a string of pearls that form all of a sudden along usually the equatorward most arc, and then it expands. This arc expands rapidly and grows very, very bright. Gets dynamic. It moves around a lot. This is when you get the dancing auroras. That nitrogen fringe. Those particles have really high energies. This is called the expansion phase. So the onset is usually 1 to 2 minutes. The growth is usually a few hours, and the growth before the onset, rather. I want to make that distinction. And the expansion usually lasts only 15 to 30 minutes. It's pretty short. If you think about a whole night, 8 to 10 hours of darkness, maybe 12, 16 hours in the wintertime, right? Um, really the expansion phase is only 15 to 30 minutes, and that's the best aurora. And then after the expansion phase, the aurora goes through a recovery phase. So during this recovery phase, you get pulsating aurora. It's flickering around a lot. It's actually still pretty bright and like an all sky camera. Like it's like physically bright, but to the eye, if you're actually outside, it just kind of looks like this dull haze that's sort of lighting up the sky. Like there's aurora there, but it's sort of like if the entire sky had like a white sheet of paper, or like a white sort of translucent cloth just like draped over it. Like it's visibly brighter, but there's like almost no structure or definition to it. That's the recovery phase. And sometimes this recovery phase, the aurora never actually recovers all the way till when it, actually starts a new growth phase again. So, we usually just get 1 to 2 substorms a night, but these substorms are what you really want to watch out for. And at high latitudes, these occur all the time, every single night. But, even during geomagnetic storms, these substorms occur. And, if let's say the auroral oval is somewhere in southern Canada, people in northern Minnesota are seeing this growth phase. But let's say you're in Oklahoma or Colorado or Utah, you're waiting until this aurora gets really charged up, really beefed up and active in this expansion phase. Like you have to actually wait for the substorm to happen to see the aurora from those lower latitudes. Because um, when these substorm expansion phases happen, you're getting a bunch of particles dumped into the atmosphere that have a lot of energy, and they're hitting all these layers on their way down. So you get enhancements not only in this nitrogen fringe, you can actually see the nitrogen fringe, but you can see the greens so much brighter, but you also get more reds too, right? I mean, these particles there's so many more particles. You have particles that are not only really high energy, but also really low energy too. So those particles don't make it down as far. They actually just deposit in this upper layer here. So you're going to get an enhancement all the way through the whole spectrum. So if you see the aurora get like really, really red, like really bright, tall, dancing red pillars, that's because there's just more particles coming down during these substorms. Anyways, I don't want to get too carried away because I'm already at almost 30 minutes. I'm like barely through this presentation. So I really got to chop here. But I technically have no time constraints. So could stay here as long as I want, but I'm not going to do that. I'll let you guys, take a breath. So, okay, I already kind of alluded to this, but what causes the really, really good auroral displays? After all, right, the aurora doesn't look the same every single night. It varies around. It changes. It's natural, right? Nature is not always the same, luckily. Otherwise, life would be boring. So the sun can get angry. We have space weather, right? The wind can blow fierce, can blow strong, can blow fast, right? You get thunderstorms on Earth, you get tornadoes too, you get hurricanes, you get all these sort of, different levels and scale sizes of storms, and the same thing happens in space weather in space. So really for auroras, we're concerned with coronal mass ejections or sun burps or sneezes, which launch parts of the sun's atmosphere into space. We're talking about clouds of charged particles. Instead of mucus, right? Sun sneeze, mucus, gross. We're talking about charged particles. These CMEs can be directed in any direction. They're kind of like cannon shots, like cannonballs, right? The sun is lining up these shots and boom, boom, boom. And these usually happen from active regions or filaments, and sometimes those filaments are facing right at us, and that CME is, boom, right in our direction. Or maybe it's off to the side and we see it launch in this direction or in this direction. So they're not always directed at Earth. We can see a big CME happening, and it could even be on the far side of the sun, completely 180 degrees away from us. But these explosions can be directed in sort of, any direction. And if they are directed at Earth, they usually take around 1 to 3 days to reach us. I believe one of the fastest CMEs was the Bastille Day event. You can look that up. It's on Wikipedia. And I think the CME took around like 17 or 19 hours to get to Earth. So that's pretty much the lower limit. It takes about a day, minute or day minimum, yeah, to reach the Earth. So 1 to 3 days nominally. The solar wind flowing at around 350, 400 kilometers a second, which is sort of the average, takes around 4-ish days to get to Earth. So nothing really slower than 4 days. Otherwise, it wouldn't really get here. It would just be a lump or like just absorbed in the solar wind, basically. So, anyways, um, yeah, when these CMEs hit Earth, right, it's like the big gust of wind. So, if you imagine, this wind kind of gently buffeting our planet, and we have this teardrop shape, right? The stream of water hitting a rock, flows around the rock, flows this little, or creates this little, bow shock wave in front of it. Imagine this big, surge of water comes in. Well, all of a sudden that rock is just going to get flooded, right? And luckily, the magnetosphere actually does shield us at some pressure, right? So it doesn't just collapse, but it gets pushed farther in. And some of that energy from the CME, if the magnetic fields are oriented the right way in the CME, they can couple with Earth's magnetic field, and some of that energy gets transferred in, and the aurora ovals get more charged up. And those aurora ovals can expand further equatorward. We can get big geomagnetic storms. We can get auroras all the way down to, let's say, California or Mexico, like we've seen this year already. And that's really what gives us the best displays are these CMEs. Now we also get coronal hole high speed streams. So the wind can either be really gusty, like big, fast, dense gusts of wind, or we can get these more longer duration, multi-day, sort of fast wind streams. They're not big gusts, but they're just, gradual ramp up of fast wind. These can also give us geomagnetic storms, but they're usually not as severe as CME driven storms. We're usually maxing out around a KP7 with these. That's a really big, that's a really nice coronal hole if we can get a KP7 out of it. But usually they're like KP5, KP6. So they're really great for high latitude folks like us up in Alaska, because really it seems like that KP4 to 6 is like a nice sweet spot for, you want a really nice active aurora. Usually, I mean, of course, you don't need a high KP for an active aurora, but a little bit of geomagnetic activity is sort of injected in. It's never going to hurt. So, anyways, yeah, during these coronal holes, solar wind speed jumps from around average again, like I said, 350 to 400. Can jump all the way up to 5, 6, 7, 800 kilometers a second, so pretty fast. And you can actually see these coronal holes where the high speed streams flow out of in EUV imagery. So I believe this is 193 angstroms. This is on SDO AIA. You can see these coronal holes really well in the 211 angstrom channel as well. That's the purple sun. Let me just test my knowledge here. I'm just interested to see if I got that right. Yeah, so that is the 193. So this channel is really good, and also the 211 is really good as well for detecting coronal holes. And why are they dark? Well, it's because the magnetic fields here are open. So the particles, if they're trapped along magnetic field lines, will just bounce around. They'll just keep bouncing back and forth along the magnetic field line until they reach the foot points. It's a fundamental property of particles traveling along magnetic fields. It's called an adiabatic invariant, but that's besides the point. When these bouncing motions happen, some of that energy of the bounce gets kind of lost to heat, right? So these these particles along the field lines that are closed are heating up. So in the images they look bright, right? You have closed magnetic field loops around active regions like here and here and here. But when the magnetic field lines are open, particles can just flow right out. So there's none of this bouncing motion that happens, and you get a dark patch, which corresponds to a cooler region in the sun's atmosphere. So coronal holes are not actually holes in the sun. They're just regions of open magnetic field lines. You wouldn't see these holes in like a visible light image of the sun. This is just in the sun's atmosphere in the corona. And should note that these coronal hole high-speed streams, these fast solar wind streams, as they're kind of rotating with the sun, right? So the sun's rotating here. So these coronal holes are constantly spitting out this fast wind. Well, as the sun is rotating, you can imagine this fast solar wind streams like a snowplow just pushing the slow stuff in front of it, like, hey, get out of the way. We got to go. We got to go fast. But because of that, you get this compression region called CIR, SIR that forms in front of the fast stream. So when you look at these fast solar wind streams in solar wind data, you typically see a ramp up of the density followed by a decrease in density and a ramp up in the speed at the same time. This is something that I go into detail in my beginner's guide to aurora chasing, which is on my website. It's free if you sign up for my email list. But anyways, these coronal holes can last for a long time. So CMEs are sort of like just, instantaneous, events, right? These coronal holes, you can see them coming for days, right? So it's pretty easy to predict geomagnetic activity for coronal holes. And they're like lighthouses. They can make reappearances every 27-ish days. The sun rotates every 27 days. So, we only see one side of the sun at once. The face facing Earth. So we see these coronal holes for around, 13, 14 days until they rotate away. And then we're crossing our fingers, hoping it survives. And then we might see it again, 2 weeks later as it rotates in on the other side of the sun, right? So this is one example of a coronal hole that was seen for almost 6 months, which is pretty rare. I mean, usually they last, a few solar rotations, and actually, as we go towards the descending phase of the solar cycle, these coronal holes become larger and sort of deeper. So the high speed wind is a little bit faster and has a more broad sort of or longitudinal extent, if you will. So basically saying that these holes are wider. Um, and you can get these long-lived coronal holes, usually during solar max. Right now it's 2024. We're in solar max. We get coronal holes, but they usually don't last more than a couple solar rotations. But during the descending phase of the solar cycle, you can definitely get these, 3 or 4 rotation coronal holes. And fun fact, that's actually why you see geomagnetic storms forecasted 27 days in advance on the NOAA 27-day, forecast. There's not a coincidence that the sun's rotational period is also 27 days. NOAA knows this, right? So 27-day aurora forecast, that's tied right to coronal holes. So if you see a coronal hole on the surface of the sun, or rather the atmosphere of the sun, and it gives us a G2, okay, great. In 27 days, chances are it's going to give us another G2. It could also close up, right? These holes don't last forever, obviously. Like the hole here looks a lot different than the hole here. It looks like it's closing here. And in fact, there's probably not a seventh image because it was gone on the next solar rotation. So that's why the 27-day is not always accurate, because this coronal hole, let's say this gave us a G2 or a G3, here it might give us the same thing. It might also give us a G1 or KP4, who knows? Not all coronal holes, even the same ones as they rotate back around, do the exact same thing either. But, chances are it's going to give us another geomagnetic disturbance. So if the 27-day forecast generated on July 26th, predicted a KP6 in 27 days, well, it's probably going to be pretty close, right? At least the coronal hole's there. But the 27-day generated on October 14th, it's probably not going to be right because this coronal hole looks like it's closing up. So that's why the 27-day should be taken with a grain of salt. But as we get closer to the descending phase, as we get into the descending phase of the solar cycle, you can start paying more attention to those 27-day forecasts. They might become a little bit more reliable. All right, let me just take a quick drink of water here. All right. Ooh, all right. So CME flux ropes, CME modeling, SSBCs, not going to talk about those. Also not talking about a lot of other things. But if you saw my Aurora Summit presentation, this has a lot more, as you can probably tell, because I've been spending more time on things. So I'm actually talking about more than what I was talking about at the Aurora Summit presentation. So I might be talking a little bit about CME flux ropes later, but a lot of the nitty gritty on modeling and things like that. I've done CME modeling before. I published papers on CME modeling. It's complicated. And I just wrote a blog post about how to use the Hux forecast. Definitely recommend you check that out. It's kind of a nice intro to how a lot of this stuff works, right? If a CME launches off the sun, what kind of data are being fed into the models, and how do the models run, and how do they work, and what is NOAA doing with their model, right? How does the Hux model work? What are the uncertainties of a CME impact or CME arrival time? All those questions are kind of answered in this blog post, and I'm going to link it on the official sort of version of this presentation on my over on my website. But not going to be talking about that today. So So the question that you all probably want to know is, can we predict these events? Can we predict space weather? And the answer is yes, but it's hard. Thankfully, there's space weather scientists out there that are helping us. One of my friends, Tamitha Skov, Dr. Tamitha Skov, as pictured here on the right, and she's really, really good about breaking down sort of what's going on in space, the space weather that we're seeing, and really making it approachable. Because a lot of the products that NOAA SIPSI releases, actually, I would say 99.9% of what NOAA SIPSI does is not for Aurora chasers. So a lot of the stuff that we're using on the NOAA SIPSI site, Space Weather Prediction Center site, were never intended for us. So I get a lot of people saying, "Well, NOAA uses the KP. Well, NOAA says this." Well, NOAA was never designed, was never enacted or put in place to help millions of Aurora chasers across the world. Now, do I think that they should keep that in mind? Yeah, of course. But that's just not the reality. NOAA is concerned about whether your lights stay on when we get a Carrington event. They're not concerned about whether you're going to see the Aurora in Lansing, Michigan at a KP3. So keep that in mind, is that a lot of this stuff requires a little bit of knowing what the limitations are, what the context is for these predictions and models and data. So if you don't know a lot of these nuances, well, that's totally fine. I didn't know either. And I was completely lost. But what I did is I started following people who did and who knew what was going on, people who were experts in the field, like Tamitha. I started watching YouTube videos and looking up sites and reading papers. So, it's totally fine to feel like you're over your head with a lot of the science here, or the data or forecasting or anything. But that's why you're watching this presentation, is to sort of get some more context. And also, don't just listen to me; listen to other people too. I would definitely prioritize people who have credentials, but it's nice to hear things from different perspectives. And Tamitha is just another perspective. She's way more of an expert than I am on any of this, but cannot recommend her enough for you know how to read the data and what to look out for, especially when we get big events. It's nice to have one person to just kind of watch and relax, like let somebody else do all the heavy lifting. Somebody who has the expertise. So definitely recommend checking out Tamitha's videos. Okay, one caveat with you know predicting space weather is you don't always have to predict it, right? You don't always have to have good space weather to have a good aurora. That's why we're all here. We all want to see good aurora. So this is a video I shot of some KP2 aurora, and KP, as we're going to learn later, is kind of a not so great metric to watch anyways. But it's what people use to say, oh, it's quiet, or oh, it's active, or oh, it's really, really good, right? Oh, it's a KP9. Of course that's good, right? If it's a KP9, a rising tide lifts all boats. I mean, it's an active night. But this is a KP, what is this, KP2? Yeah. I mean, to all other people, especially the people who don't necessarily know about the limitations of KP, this is a night that they might not even consider going out, right? It's a KP2. It's not anything special, but this is a top five display for me. This was insane. I mean, I saw some crazy I mean, you can see it, right? Crazy motion and crazy colors. Really, really strong substorm. I mean, the substorm was strong. And the substorm strength does not always correlate with KP, especially at these like KP 1 to 4 to 5 levels. You can get some KP 5 events that have some really weak and crappy substorms, and you don't really get those big bursts of aurora that you're looking for. You might just get instead of a big burst of aurora, you might just get like a steady trickle. And it never gets to that great level. It might get good, but it never gets great. So, sometimes it's really not about the space weather. It's just all about being outside, just being patient, just watching the data, just look at a webcam, right? The Aurora does weird things. I mean, that's why I'm into this stuff, right? If it was all the same all the time, then I would have a PhD, I'd have a Nobel Prize, and life would be great. Nature would be solved. We'd have we could burn every textbook because we would know everything that there would ever need to be known about space physics. But the Aurora is different every single night, and it constantly just does weird things. So, that's really scientific, right? But basically, the gist is that substorms happen. We know about substorms, but not all substorms are created equal, and substorms can happen. Really good substorms can happen under relatively weak solar wind driving and relatively weak space weather conditions. I guess the equivalent of that would be like a rogue wave, right? All of a sudden you could, let's say the wave forecast is not that high, but all of a sudden you get this rogue wave out of nowhere, and it's great for surfing, right? Kind of the same deal. Or like, all of a sudden, let's say that the chance of tornadoes one day, I'm from Minnesota. This happen all the time, right? The weather person says, yeah, chance of severe weather is 10% today. And I say, okay, that's fine, but you never know, right? Of course, we all know you never know. 10% is not zero. But if we see KP1, right, for some reason we think, well, that's a 0% chance of a good aurora, but you can get a tornado at a 10%. It's just not likely. Same thing with the KP1. I mean, you might say, okay, well, it's not a KP7 or 8, but you could still get a nice substorm. So, anyways, can we predict the aurora? Well, not really. Kinda, I guess, but it's hard. And I would actually say we really can't beyond maybe like a couple minutes, 3, 4 minutes, something like that. But really, everything else is just a guess. I mean, even anything is really a guess. But I would say around a few minutes, yeah, we could probably tell what the aurora is doing, but that's not that useful. People want to know what is it going to do in 3 days or a week or in a couple hours. Well, that's really hard. So let's get into it. Aurora chasing is all about finding out what tools you want to use, and if you're the KP, if you're a hammer, everything looks like a nail, right? So the KP is not even on here because it should not be ever used, really. KP is pretty much useless. I recommend using any of these screenshots here. They all have some sort of value. So, Ovation Prime, real-time solar wind, GOES magnetometer, the Aurora electrojet index. And by the way, I've been saying this all throughout the talk, but links to all these data sources will be provided in the web version, the posted version of this talk, which you'll find on my blog. So right now it's not in here because I have not made that version, but I will work on it right after this and I'll post it along with this recording. So let's just talk about the KP index. I'm going to have a whole blog. Actually, I already do have something in my blog about this, but it's also in my beginner's guide ebook. But just to sort of drive home the point that the KP index is not great, it's really just measuring global average geomagnetic activity. It's like saying, okay, what is the rain forecast right now in Washington, D.C., and then saying, well, 3 hours ago, the global raininess index was a 3. Okay, well, I want to know what it is right now. I want to know what it is for Washington, D.C., and I don't want it to be averaged. I want it to be specific. I don't want a global, I don't want a global raininess index. That doesn't help me, right? And like, this is the same thing that happens with the aurora. I mean, you can't say the aurora is happening the same everywhere around the world. Like you can't say it's just a 3 when you might have a substorm over here just starting, and over here it's completely dead, right? Until the substorm moves and expands across the oval. But like that instant that the substorm is firing up, I mean, it might be, let's say, a 20 over here and a 0 over here, and that's not a 3. It doesn't even average out to really anything meaningful. So, anyways, yeah, KP is just pretty much useless. And also, to add insult to injury, to keep twisting the knife, these observatories that are measuring the KP, so KP is a magnetometer based index. So, what you're doing is you're taking literally, they look like film canisters and they're buried 6 feet underground and they're reading magnetic field wiggles in Earth's magnetic field caused by disturbances, in Earth's atmosphere. So due to some fancy electromagnetic laws, Faraday's law, for example, induction, you can get wiggles in magnetic fields on the ground from wiggles of magnetic fields in the air, in the ionosphere, and in currents in the ionosphere, in the auroras or other phenomena. But these magnetometers are not measuring that because they're in the mid latitudes. So, you don't usually see the aurora down in, I guess, what is this? I don't even know what you know, what these names are, but Central Europe and, down here, I don't know what this is, like Ottawa, Fredericksburg, right, or something. I don't know. Anyways, the aurora is not usually down there. So why are we measuring this area, right? These areas don't really become active until the aurora oval starts moving down. Um, but yeah, I mean, for trying to figure out what's going on in Alaska, for example, you really want magnetometers that are underneath the aurora oval when it's quiet. And we're going to get to an index that does that. But KP is measured from 1 to 9. I guess I should actually give some information about KP for those of you who don't know. It's measured from 1 to 9. 1 is the least active, 9 is the most active. It's the max. And during the May event, we may have actually eclipsed a KP9 if we could actually go higher than a KP9. And I'll show that in another slide too. But the KP measurements correspond to the G scale, which is a NOAA Space Weather Prediction Center geomagnetic storm severity scale. So G1 corresponds to KP5, G2 is KP6, and then so on and so forth. And actually, they're going to be redoing the scales. So take what I just said about the G scale, and actually, it'll be interesting to go back and watch this, a couple of years later and figure out whether or not we've changed it because there's talk right now of changing the scales. Actually, they will be changing the scales, and the G scale may be discontinued. We'll see. A lot of things rely on the KP, including hotels. This is Chena Hot Springs, including the NOAA KP forecast, the 3-day and 7-day, 27-day forecast. I don't think there's actually a 27 or rather a 7-day, but 3-day forecast, 27-day forecast. 3-day forecast is kind of like just throwing darts at a wall. Not really useful. This big, Aurora donut, the red donut that we all see people post, the news media goes nuts with it and makes their own version with even more flashy colors somehow. I don't know how it could get worse, but it does. And yeah, the KP is just baked into so much, including your apps too. I mean, even Space Weather Live. I mean, Space Weather Live is pretty much just a data, here's a data app. They don't tell you a whole lot of, analysis. But yeah, the KP is, I mean, it's right front and center, right? You open the app, it's boom, it's right there. And really, it's like, yeah, I mean, I guess if you're just an enthusiast, you don't care about the Aurora, sure, KP is kind of fun to look at, but it's not really great. It's not really great for Aurora chasing. It's just not. Here are some limitations. It's a 3-hour average of activity. Auroral substorms cannot be captured by KP since they only last 15 to 30 minutes. And it's a 3-hour average of past geomagnetic activity. It's delayed. If something happens now, KP is not going to catch it until the next recording of the data. So it's not real time. So this is really important after CMEs. Usually the best auroras after CMEs are right after the CME impacts. KP is not going to get it. It's not going to have enough time to react. It's a global average. Like I said before, that's wrong for many reasons. The magnetic stations aren't even in the auroral oval. What's the point? And predictions are more like best guesses, especially in the 3-day forecast. You see a CME, forecasted to arrive, and you see like it's a KP5, and it's a 7, and it's an 8, and it's a 4, and it's a 3, and it's a 5, and a 6. Like, what does it even mean? Like, what the CME does is anyone's guess. You can't forecast a KP not until the CME actually gets here, right? So those 3-day forecasts, I just don't even look at them really, unless it's like, oh crap, we went from a KP3 to a KP9. I'll start paying attention. But I'm not going to be like, oh, it's a KP9 from 0 UTC to 3 UTC, and then it's a KP4 from 3 to 6. So I'm not going to go out at this KP4. I'm going to wait for the next KP9. Like, it's not, nobody can do that. That's more just like, we think that maybe it'll get better once the CME hits, maybe. And then we're just going to put some numbers up there. I mean, yeah, unless they have some magic model that is going to win them a Nobel Prize and it's going to change the field forever, and some revolutionary new supercomputer can run this in 10 seconds. Yeah, anyways, I digress. Okay, here's the problem with averaging the values. I think this was a little bit confusing to people during the summit, so hopefully I can elucidate a little bit better. This might have been my own fault for doing it like this, but let me just kind of recast this now. So this blue line here sort of traces out the actual raw reading from a magnetometer in the KP chain. So this is just showing for one little section. This is the line here. You can see it has lots of wiggles. It goes from a low value to a high value. There's peaks and valleys and mountains and all sorts of stuff. Lots of variability. The Aurora is probably doing crazy things, or something's going nuts, right? Magnetometer is going all over the place. At all these red arrows is when the KP was recorded for the previous cell's activity, or 3 hours worth of activity. So at this red arrow here, all this blue data was averaged out, and we got this up here. Okay, so this is our average KP value, is up here. And then for all this, we get this one. For all this, we get this one. So this one's terrible. I mean, look at this. This KP value comes in here at 21. As I don't know what number this would be, but it's higher than the rest, right? So let's say this is a 6, and this is like a 4, this is a 5, and this is like a 3 or something. I don't know. You get a KP6, but the activity is pretty low. I mean, the activity is not a 6 anymore, right? If this is a 6, the activity is all the way down here. So this isn't even accurate, right? This is the problem with KP, is that by the time that value comes in, the data is already old. So there's also HP30, which is kind of like a smarter KP. So this is actually showing the KP, HP 90 and 60, and then 30, which is sort of this red thin bar here. It uses the same magnetometers as KP, so it's flawed still because it's not really sampling the right areas. And it's also still a global index, it's a global averaging, but at least it's every 30 minutes. So you can see, you can actually see here, this is on the May, I think this is, yeah, the May 10th storm of this year. The HP30, now this is not the KP, right? The KP maxed out at a 9, but the HP30 went all the way to 11.3. So if it was sustained, I don't actually know what the averaging looked like here, but we're maxed out at a 9, so we don't know what it would be anyways, because we can't go higher than a 9. But this actually might have been higher than a 9. And actually, let's see, this is every 30 minutes, so we're looking at 6 bars for 3 hours. So we have 1, 2, 3, 4, 5, 6. Yeah, this probably would have been like a KP 9.5 or maybe even a KP 10. So, um, what's the point of having an index that maxes out, right? If you go higher than that, especially when you're talking about these big storms, I mean, you have to know how strong they get. So, anyways, can you tell that I don't like the KP? I hope it comes across. So, okay, the Aurora Electrojet Index. I don't actually have a picture of the magnetometer chain here, but if we go back, it's in this area here. So it's right underneath the Aurora oval. So it solves that issue with the KP. It's continuous. Okay, great. We don't have to wait every 3 hours for a new value. It also is more granular. It's not just 0 to 9. It goes from 0 to 2000. And it responds to substorms because we're actually in the Aurora oval. So yay, that's great. The only problem is that it's still an average, so it doesn't quite capture really, small variations. It sort of takes some time to, once that substorm spreads out a little bit and it starts covering more magnetometers. Okay, AE starts to sort of, kick in, right? So the substorm might actually happen here, but then as that substorm expands and during the recovery period, you start to see the graph actually rise. So it's really easy. Higher number equals better, just like the KP. And there's some thresholding you can do, although I tend to, just be a little bit careful with this. Like, caveat is not all thresholds work, especially the KP and the view line stuff. Don't even get me started. But I like to say, around 500 nanotesla is when I start checking the US-Canada border cams. There's webcams in Minnesota, Michigan. Once the AE is around 500, that's when we're getting a little bit of a substorm. That's maybe strong enough for naked eye visibility down there. And then 1,000 plus is really good for like the central US. I think the May storm was over 2,000. So this index does saturate along with the KP. It's kind of funny because it just goes off the charts. It actually keeps reading. It just is not, it's just, this chart is not really designed for these high values, like over 2,000. Real-time solar wind is sort of outside the scope of this talk, but you really want to watch for negative or south BZ because if you've ever done this, I hope we all have. You take two magnets, bring them close to each other, north and the south, boom, they start attracting. You can feel that attraction force, just like the solar wind, right? It's that gust of wind coming, or that wind coming in. It has a magnetic field with it. And if it's oriented south, BZ south, look at the diagram in the top right. Earth's magnetic field is pointed north all the time in space. It's always flowing north. South and the north come together, boom. Energy can be transferred in a process called magnetic reconnection. And that energy, those particles from the solar wind can get dumped, can penetrate our force field, can go down and into the auroras and can light things up, essentially. So that's why we like South BZ. South and north attract, boom, energy gets transferred into the aurora. Now, when we have a really extended period of South BZ, like we're talking 3 to 4 hours, those aurora ovals start to march towards the equator. And then sometimes And these things called BZ south turnings, when the BZ goes from south to north and it flips really quick, that can kind of shock the system and we can get those substorms. Now, substorms can be triggered really by anything. This is an open question in the science field. This is not something that I can actually confidently say, but these south to north turnings have been proven to result in substorms. So sometimes if you see the BZ south for a long time, you're like, oh, I wish the Aurora would have just do something like the BZ south. Like why isn't it kicked up yet? Why haven't we seen that burst? It's because you're waiting for the BZ North to come in. So that's the one case where we're actually waiting for a BZ North, and we're like, oh, I hope it turns north. If it's been south for a long time, it's good. There's a lot of potential for the Aurora, but it just needs that little kick to really get going. And sometimes it's like you just need to throw a bucket of cold water on it and just say, hey, let's go. Let's get going here. And that's what that BZ North is. So yeah, in my ebook, got a bunch of stuff. This is my second edition, by the way. Third edition is coming in 2025. So if you're subscribed to the email list, you'll get it for free. Don't worry. But if you're not, make sure you subscribe. You'll get the second edition for free right now. But there's tons of information about how the solar wind works, and also more about how to read the solar wind, because I did not get into that in this presentation. Just not enough time. Already going way over. I'm already an hour in. So yeah, I gotta cut things off. But I mean, this is fun. It's just more content for you all. So, and I'm enjoying it. But anyways, yeah, this is the extent to which I'm going to go into solar wind in this talk. But check out my beginner's guide for more info. So Ovation Prime, the Ovation model, the Prime is sort of the newest version, but it's a model of the Aurora based on the solar wind data. You take all this solar wind data, the speed, the IMF, BT, the strength of the magnetic field, the BZ, shove it into a fancy equation, mash it all up, put a fancy color bar on it, and plot it as a sort of statistical average of what the Aurora would do. And you get ovations. So it's not really the Aurora. Can't detect substorms, just a model. What you see is not really the Aurora, it's just smoothed out. And your app is going to say, oh, you have a certain percentage of seeing the Aurora right now in your given location. Well, guess what? They're taking the ovation model, they're taking this probability, and they're turning it into a piece of text and they're serving it to you. That's all you're seeing is this model in just a different way. So this is not real. This is a model. Yeah, enough said. It's not okay. I should say it's nice to use though. I mean, if you don't know how to read solar wind data, the more gigawatts you see, the better the solar wind probably is. I mean, it's not going to capture the things like the BZ North turnings and things like that, but it's not going to capture the substorms, but it is going to show you when things are generally enhanced. So of course, if it's like a 50 or a 60 gigawatt, the BZ's probably been south for a while. It's pretty far south. You have a good chance of seeing the Aurora. So I mean, it does correlate pretty well, but don't get hung up on like, oh, I'm not in the red, or oh, I'm not right on the green yet. I'm not going to see it. It's not. It should never be taken that literally. So just keep that in mind. Forecasting these auroral substorms, I keep mentioning the substorms, but this is what you really want to see. You really want to see the Aurora just go nuts for 15, 30 minutes, right? You just want to see it explode and just that active motion of bright colors. And how do you do that? How do you see these substorms? Well, if you know me, I'm on my soapbox now, and should have had this at the start because now I'm starting to get tired. It's like 11 p.m. right now, and just got done with a 10-hour day of reviewing proposals. So, anyways, look at my website. I got a whole article on how to read the GOES magnetometers. These magnetometers, just going to give you the quick rundown. These are geostationary satellites over North America. You have the red one, which is on the East Coast. The blue one is on the West Coast. They sit at 6.6 Earth radii in geosynchronous orbit, which means they are in, look at this this leftmost video. They are in this area right here where my cursor is. Let me get rid of this. They're in this area. So as you can see, when we get these substorms, this is actually the physical process which is taking place. These field lines are turning from really stretched to really straight up, right? It's like a rubber band. You have all these particles being loaded into the magnetotail. It's charging up. The Aurora is charging up. All these particles are just waiting to be released. It's like the BZ has been south for 4 hours. You have all these particles that are just waiting in the wings, ready to be released. These field lines are stretched out. It's like a rubber band. You're pulling it back, pulling, 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 pulling. If you imagine the rubber band starts out from a perfect circle, right? You buy it in the store, it's a perfect circle. You start stretching it out. Imagine you're holding a big slingshot of particles at one end. Boom, you let go. That rubber band comes flying, 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 then turns that perfect circle again. Gauss magnetometer is measuring how round that rubber band is, how round the field line is with all the aurora particles. When it gets lower and lower on the graph, that means it's stretching out further and further and further, more charging. As soon as it starts spiking up, that's when these field lines are racing. You'll see it here. Boom, field line starts racing back to the night side and it becomes more what's called dipolar. It becomes more like a perfect bar magnet where it's up and down. So the BZ component, the Z component, how up and down that field line is much larger. That's why the graph goes up. Graph goes down, field line's shrinking, it's getting more compressed, more elongated, more stretched. Graph goes up, boom, particles are slingshotting back, and field line's becoming more dipolar. It's called a dipolarization or bursty bulk flow. That's what's responsible for the substorms. And I've correlated that actually. Perfect timing too. Watch this. This is an all sky video of the aurora from Fairbanks. I've got a green line, same line in the plot as the same line in the aurora. You'll see this now. Boom. Aurora started. So actually the this is October 7th. You remember this night. Oval was so far south. So actually um, it's a little bit before the spike, or rather, sorry, it's a little bit after the spike that you see the brightening. But yeah, basically, right when you see the spike is when you see this big burst of aurora. So you can go out when you see these spikes happening and Gauss magnetometer, just go outside and start looking up. You're going to see the substorm. It happens like 99% of the time. It's not perfect. Nothing's perfect. It's all proxy, but Gauss magnetometer is pretty great. So got a whole article on my website. I need to actually redo that because um, it's really it's a great tool, right? I started using this last year. There was a scientist by the name of Dr. Christina Lynch that was on sabbatical in Fairbanks. I went to Poker Flat with her and just kind of hung out. And she had Gauss magnetometer pulled up on one of the monitors, and she was like, "Oh, I'm just watching the aurora." And I'm like, what the hell is that?" I was like, "What are you using?" Because I'm used to using Ovation and Solar Wind Data. And she's like, "Oh, this is Gauss." And I'm like, "What are you talking about?" And then that's when I was introduced to Gauss, and I've never looked back. But ground truth data is still the most important. All this stuff is proxying auroral strength, but you want somebody actually outside taking a photo of the aurora and showing you what's going on. So that's why Facebook groups, my Instagram alert channel that I have set up, they're so helpful, right? You actually have somebody outside telling you, hey, we're seeing the aurora in XYZ ABC locations. And you can track auroras with Aurorasaurus. If you see the aurora, make a report. The data are made available for scientists and help validate aurora models like Ovation. So looking at where Ovation is predicting where the aurora can be seen versus where people are actually seeing the aurora is really important to help scientists better inform the models and what they're going to be doing to make those models better. So you can actually help the science. And you can also become an ambassador if you're really into this stuff. If you're a really avid aurora chaser and you're for example, a leader in a Facebook community, or, just honestly, for just anybody who's obsessed about the Aurora and has a passion for this, there's a form you can submit online through Aurora Source to become an ambassador and start repping participatory science, and getting people involved in the fight to make, or just to sort of further our field, because space physics and aurora science is really cool. I mean, we study things through analyzing imagery. So people submitting their images to us, to scientists, to professionals, projects, what have you. It actually does make a difference. I mean, there's been so many discoveries recently that have come about because aurora chasers are collaborating with scientists, and that just leads to some really cool things. And really quickly, why is this year so strong? We're in Solar Max. It was just declared officially, uh, I think last week, that we are officially in Solar Max. So Aurora should be good really until 2026, 27. We should have lots of space weather for those mid-latitude folks. And then, of course, the aurora ovals are out all the time. So it's not like the auroras disappear at solar minimum for high latitudes. So, yeah, sun's most active it's been since 2001. So get ready. We're in for a good one. So here are like two methods for how to see the aurora. First one is um, traveling somewhere to see it. Second method is seeing it in your own backyard. This is kind of like two regimes of aurora chasing that I would tell people like, okay, if you're in Alaska, you have one track, and if you're in Minnesota, you have another track, and if you're in, Texas, you're in the Minnesota track, but you're just looking for more stronger events, basically. So let's get into it. So, best time of the year really is, the equinoxes. We have more substorms for some reason during, the equinox months or the months surrounding the equinox months. So, that sort of Feb to April time range, and also August to October. Scientists are not sure what this is caused by. It's called the Russell-McFerrin effect. So, roughly, around the equinoxes, it's, a little bit more active. It's definitely appreciated at higher latitudes. It's not like it's night and day. Like you don't not see auroras during the solstices, but during the equinoxes, just the littlest bit of activity seems to just spark things up. So during the summer, not a good time to come to the northern hemisphere high latitudes to see the aurora. We're completely too sunny, too bright to see anything. Sun's up for 23, 24 hours a day in Alaska. Don't come. You're not going to see anything. So enough said. Um, Moon phase is very subjective. I'm a fan of new moon or like a 25 to 50% moon phase. Other people like full moons. If I'm doing a workshop or a tour, I really like full moons because people underestimate how dark it is and how hard it is to go from looking at your phone in the car to stumbling around outside and trying to figure out where you're going. I've had people just like become very disoriented and they can't see in the dark usually. So having a full moon in the sky, even though it sort of mutes the fainter auroral forms, it actually lets you see more colors in the aurora. I have a blog article on that. And it helps you see in the dark, and it helps you see what you're doing with your camera. You don't need a headlamp. When you have snow on the ground, it's just like daylight. It's so bright. And it's kind of nice, actually. It's like a nice comfort to have. So, yeah, new moon and, first quarter, third quarter new moons or moons are helpful for photography. It gives you more contrast. It does make photographing like in the summer, like without snow, pretty difficult because you have like no reflection on the really no reflection on the ground when the aurora is dim, so your foregrounds are super dark. And I like to underexpose just in case the aurora gets really really bright. So it's hard for me to maintain a good like shadow exposure that's not completely clipped. So snow definitely helps with that. You get some reflection of the green aurora on the snow during a full moon, but or a new moon, sorry. But yeah, it's nice to have contrast in the sky with with a new moon or a first or third quarter moon. I'd say really like a half moon. For half moon, to first, which is like a first quarter, third quarter, kind of a sweet spot. You get like a perfect blend between, okay, I can, the landscape doesn't look like it's daytime, right? Which honestly, I don't like that. So, I want it to look like it's dark, but I also don't want the shadows to be completely clipped. I want to actually see something in the shadows too. So that's kind of my favorite time. It's like the first and third quarter moons. This is really important is that, the aurora is not visible at every single time of the night in Alaska. It's just not. During quiet conditions, you might get the aurora coming out 10 to 11 p.m., lasts until 4 to 5. But, it's not out at 6 or 7 p.m. like people think, right? They come here in December, they're like, oh my God, we got 22 hours of darkness. This is going to be great. And the aurora doesn't come out till 11 p.m. because the space weather is pretty quiet, and then they go to sleep. They're like, oh, I guess tonight's a dud, right? We're not going to see anything. And then it was out and they were just asleep. I mean, I've lit like this is in December. Um, I've been flying out of Fairbanks and it's been clear every single night. Space weather's been pretty quiet. So the aurora's only been out for like, 4 hours, 11 to 3. And I'll be in line with people from, other places visiting Alaska to see the aurora. This is like in TSA, right? And, they're complaining. This happens all the time. But I remember this one time this woman was complaining. She was like, just to anybody in the line, she was like shouting. She was mad. She was like, I've been here for 2 weeks. I haven't seen anything. Been here for 2 weeks. It's been cloudy. The nights it's been clear. The aurora's not been out. And, maybe this was mean. Maybe this was me being kind of an a-hole. But I showed her a picture of the aurora from literally like a few hours before. Because this was like one of those like, 2 a.m. flights. out of Fairbanks. So I showed her a picture of the aurora. It was very faint, but it was there from like 2 or 3 hours before I'd gotten to the airport. And I was like, oh, it was out tonight. Oh, and it was out last night too. And I showed her a picture from 2 a.m. And she's like, oh, I didn't see that. When was that? And I was like, oh, it was at like 2 a.m. We're trying to see the aurora. Regardless of if you're in Alaska or Iceland or Norway, it's not out every single hour of the night. There's some shift. Alaska's kind of on the later end, right? Auroras usually peak around like 1 to 2 a.m. is kind of when those substorms happen in Alaska. In other areas of the world, those substorms might happen usually around like 11 p.m. to 12 a.m., but still, it's not out all the time. So just stay up, drink some coffee, get adjusted because, yeah, I mean, the aurora is not out at every single time that it's dark enough to see the aurora. So, yeah, that's a big issue for tourists here in Alaska. Where in the world is best? There you go. Forecasting the lights under the auroral oval. So this is sort of that track one. Is it really chasing the aurora if it's out every single night? I don't know. Some people would say I'm spoiled, but really you're just looking for clear patches and you're really just looking for any sort of activity that will turn your auroral display from good to great. It's always going to be out, but if you live at high latitudes, you're like, okay, well, I've seen the aurora 200, 300 times now. I'm really looking for like the shows that wow me, right? So like this video here was a show that wowed me. This was a KP7. Now it's not always that the high KPs or like the really active geomagnetic conditions create really active auroras, but it tends to be at high latitudes that a coronal hole high speed stream, even if it's like a minor storm, will just give you some spectacular auroras. I think the best ones I've seen in Alaska are like KP 2 to 4. And some really good displays at higher KPs too. But there is a point when, the activity is so high that the auroral oval is just south of you and you're just waiting for those substorms for something to come north. Because when the substorms happen during this expansion phase, you get this poleward expansion where the aurora just kind of flies north. So anyways, yeah, you can, sometimes have auroras that are so far south that you're just waiting for these substorms to poleward expand and bring the aurora over your head. So this is kind of what happened on this night. We were just kind of watching the aurora bubbling to the south, and then eventually we did get substorms. But by the time they got to our latitude, they were kind of out of energy. So they weren't as active. They were just very bright, but they weren't super active in terms of like motion and things like that. So um, yeah, it's very possible to be too far north to see the aurora when you're up in Alaska or really other places underneath the sort of quiet time auroral oval. So here's my my high latitude aurora chasing workflow. And exactly what I just said, the aurora will be out, but when will it substorm? You're looking for those 15 to 30-minute bursts of auroral substorm expansion activity. And then also, will it be a weak substorm or a strong substorm? And you can check that with the GOES-MAG plots. Is it really, really far down, really plummeting, or, is it sort of a quiet time curve, for example? Is it just, normal conditions, right? And then, of course, checking the webcams, you can sort of understand that growth phase, right? If you're seeing the aurora in that growth phase, okay, we know that something's going to happen. Maybe we don't know when, but we know that the aurora is primed. It has not gone through a substorm expansion yet. It's in that growth phase. So we can check that as well, the webcams, and then just go out and wait for a substorm. But of course, the aurora doesn't just happen in Alaska. It's graced the skies of so many mid-latitude areas. And you can tell when it's about to happen. On different time scales, really the hours to minutes time scale is the most reliable, really the minutes part of this. But I've already talked about these forecasts. The 1 to 3 day, I just want to emphasize, should not be taken as gospel, especially on CMEs. Coronal holes are relatively easy to forecast. So I mean, if you see a KP 5 or 6 from a coronal hole high speed stream, yeah, chances are it's probably going to hit us. It's probably going to hit us and probably going to give us some good activity. But a CME, how many times have we seen a CME not deliver or a CME not hit at exactly the time that they forecast? It happens more often than not, actually. So why would you take these KP forecasts with any level of certainty or confidence? Honestly, if you see a KP forecast and you see you see a 3 day forecast, keep that to yourself. Don't post it anywhere because it does no good to propagate this information. Like people will just get all bent out of shape over seeing a big red donut saying, okay, well, tomorrow night I'm going to see a KP9 because that's what's forecasted. Well, what if the CME comes now, 12 hours earlier? Let's say you're posting it 12 hours earlier. What if it comes the next day? What if it never hits? I mean, there's been some Halo CMEs, right? Ones that are directed right at Earth that just poof, magic, just go away and we never see them. So, yeah, these 3-day forecasts, yeah, not great. So here's my mid-latitude aurora chasing workflow. Um, it's probably only going to be out if activity is enhanced. So what's enhancing the activity? Is there anything coming? What's the forecast, right? Of course, I just said don't rely on the forecast, but if there's something forecasted, it means that there's something supposedly on the way. They're not just going to put out a KP9 without a good reason, right? Or a KP7 or something, right? It has to be some sort of forecast due to some sort of space weather event, like a coronal hole high speed stream, a CME, whatever, that's on its way or going to be impacting us soon. So what is that, right? When is it coming? Start looking into it. Is there a forecast of geomagnetic activity soon? What's the timing of the forecast? Was it right? Right? Did the CME ever come? Okay, it hit. Now what? Right? Let's say it just hit. Okay, let's start looking at the data. Is it going to be cloudy? Okay, impact happens. Okay, so yeah, got to check the clouds too. If it's going to be cloudy, then just leave everything in the camera bag. Don't charge your camera. Actually, always keep your camera charged, but don't be setting alarms at 12 a.m., 1 a.m., 2 a.m., 3 a.m. Like just okay, it's going to be pea soup. It's going to be storming or snowing all night. Blizzard warning. Yeah, you're not going to see the aurora. It sucks. That's Mother Nature, but that's always something to check too. It's like I get excited all the time. I get excited all the time seeing a KP 6-7 due to CME, and then I check the clouds and it's like, okay, I have no chance. So at that point, I mean, I'm addicted, so I'll still check. I'm a junkie, so I'm still going to check. But if you're a normal person, maybe you just sort of, okay, I'm going to actually have a nice night out at the bar with my friends, or watch a movie, do whatever you want in your free time. That's not stressing out over aurora data because it's cloudy. So okay, impact. How does a solar wind look? Right? Go to those data streams I was talking about. Solar wind, ovation, especially GOES mag. Is it charging? What's the substorm condition look like? Are we going to get a good one? Is it charging up? Is it spiking? What do the webcams look like? Are we seeing the growth phase? Sometimes it's hard to see the growth phase if you're south or further equatorward of the aurora oval. You really can't see those east-west aligned arcs. But scroll back through time. Was there a substorm expansion phase earlier? Now you see the recovery phase. If you see GOES, it spiked earlier. Now it's not really going down anymore. Well, maybe the activity's done. Is there a BZ turning coming in? Like all these things, right? Trying to figure out if there's going to be a substorm. And it's all up to you. This is probably the most important side of this whole thing. What do you want? Do you want to see the aurora only to the naked eye? Do you want to photograph every aurora? Do you work mornings? Like, how you interpret the data and like what are your tolerance levels, right? That all depends on you. I cannot tell you, okay, well, go out if you see the ovation at 50 gigawatt, or you see the GOES mag at 20 nanotesla, then go out and like start paying attention. Like, I mean, first of all, you really can't say anything definitive about any of these different things, right? 20 nanotesla and GOES, well, you might not ever get a substorm, even though it's really charged. Might just trickle, the particles might just trickle in, right? It's rare, but it does happen. So you can never say anything definitive about any of this stuff, but especially when it comes to like, what do you want? Like, do you want naked eye? Do you want to see really great colors? Like, do you want to photograph every single thing? If you want to photograph every single aurora, then you should just be watching substorms every single night, checking the data, checking the webcams, because you might get aurora every single night from like northern Minnesota, southern Canada. I mean, during the substorms, like the aurora oval might be hundreds of miles north of you, but it might flare up and you might get those reds on the tops of the aurora, which might, show up as a little itty bitty little glow on the northern horizon. And like, that was me. Okay. That was me when I was living in North Dakota. I was chasing every substorm. So I get it. There's nothing wrong with that. But if that's you, then you're going to be watching the data way more often than if you've seen the aurora for 40 years and you're just looking for the next May 10th and the next October 10th storm. Well, if that's your case, then you're probably not going to start paying attention until NOAA says that there's something coming, right? You're probably not going to get a May 10th storm actually, I'm going to tell you, you're not going to get a May 10th storm just out of the blue. Like, we saw nothing coming, and then all of a sudden, boom, just suddenly we have a substorm that's sending the Aurora down to Puerto Rico. I mean, yeah, you're going to be taking a little bit of a different approach. So, what kind of Aurora chaser are you? Yeah, look for something with low light pollution. You can see the Aurora in the middle of the city during a substorm, but during the growth and recovery phases, the Aurora is a little bit fainter. So, portal 4 to 1 is usually good. Lightpollutionmap.info is my light pollution map of choice. Everything linked in the final version of this talk, as I said earlier. What do you look for? This really goes down to where you are, how good your eyes are, if you have a camera with you, etc. Aurora can look very different depending on where you are and the activity. If you're in a substorm, it might be very easily visible to the eye, and you might be able to see naked eye colors. If it's a growth or even recovery phase, it's not going to be the same. So just keep that in mind. Auroras do not look the same at mid versus high latitudes. And red glow is really common, especially during substorms. The tops of the aurora just get really, really bright with red aurora. Due to the curvature of the Earth, you're looking at the tops of the aurora, the red aurora, so you're just seeing a red glow. And I actually saw the aurora from India this way. During a really intense substorm, I was able to see the very tops of the red aurora, likely above 500 kilometers, but so many hundreds of kilometers north of me that was happening. So I was able to see those red tops due to the curvature of the Earth, sort of looking at that. So that's a schematic here on the left. Aurora photography, I got tons of info on this on my site. And if you're at the Aurora Summit, this was already presented on, at length in various forms. Eyes versus cameras, got a blog article on this as well. And yeah, looks very different. And there's a lot of nuances to it. It really gets boiled down to the colors are really there, right? It's not Photoshop. It's just that our eyes are not designed to work in low light conditions. So you either need a really bright aurora to see the colors usually, or you need a full moon in the sky to help activate the cone cells, which let you see color but require a little bit of light to activate. So your rods are what give you low light vision, but it's only in black and white. And a really bright aurora will allow your cones to activate. You can start seeing the colors, and everyone's eyes are different, and we all see colors differently. So I've been next to people while out aurora chasing who can not see the colors I'm seeing, and who are seeing purples instead of reds, which I'm seeing, and they're seeing the blues. I'm not seeing the blues. I'm seeing the greens. They're not seeing the greens. Like, it's such a varied and wide spectrum of experiences that it's pretty inappropriate to say, oh, well, the colors didn't look like that. And you can't see. Like, telling other people that they can't see what you saw is just not okay. Our lived experiences are all different. So, just because you cannot see the colors does not mean that everyone else can't either. And I've actually had friends that have discovered that they're minor red-green colorblind because they cannot see the greens and auroras. So might be worth checking into if you've never seen the color in the aurora and you've seen like the May 10th or the October 10th shows. Go get checked. I mean, that's a legitimate possibility that you're actually colorblind, which is fine. I mean, nothing wrong with being colorblind. It's just not everyone sees colors the same way. So yeah, that's it. This was definitely a marathon of a presentation. I'm almost at an hour and a half here. But I hope that you all enjoyed. I could talk about this for an entire day. I think it's actually my body that would give out before my mind would, because I'm tired. I mean, talking for an hour and a half is a long time. So definitely prefer you to send me an email and ask any sort of follow-up questions you have after this, or read the blog post, or better yet, download the ebook. I have lots of information there. So with that, thank you so much. I will have a version of this presentation with clickable links, resources, tons of other stuff, all linked in my blog post. I'm uploading everything to Zenodo. So if you want to cite it in sort of any formal way, you can use a DOI, digital object identifier. So with that, thank you. And yeah, definitely send me a message if you thought this was helpful. Always like getting those as well. So yeah, thanks so much. Bye.